What if I told you the sun, our life giver, is slowly but surely changing into something unrecognizable? It's not a sudden explosion, but a million-year transformation that will fundamentally reshape our solar system. How will these cosmic shifts impact life as we know it, or will life even exist to see it? Imagine a future so distant, yet so certain, where our familiar sun is no longer the star we know. We're talking about a million-year forecast, a journey into the profound transformations that await our solar system. Prepare to have your understanding of cosmic stability completely upended. Forget tomorrow's weather. Let's talk about the sun's forecast for the next million years. Our star is on an epic journey of change, and it's not just a scientific curiosity, it's a cosmic evolution that will dramatically impact everything we hold dear in our solar system. Are you ready to see how life adapts or disappears? Focus on the subtle, early shifts within the sun itself, core temperature fluctuations, minor luminosity changes. In the earliest stages of the sun's long-term evolution, the most revealing signs are not dramatic surface events or explosive outbursts but delicate internal imbalances that occur deep within the stellar core. These fluctuations are incredibly subtle, often unnoticeable from an external standpoint, yet they signal the gradual changes in the sun's hydrogen fusion environment. As hydrogen is consumed and slowly replaced by helium ash, the core contracts slightly, increasing its temperature by fractions of a percent over spans of tens of thousands of years, an almost imperceptible process on human timescales, but one that steadily pushes the fusion rate upward. Such tiny adjustments create minor luminosity changes, typically so small that only sophisticated heliophysics models can predict them. Yet these incremental shifts accumulate over millions of years, subtly altering the balance between radiation pressure and gravitational pull within the sun's interior. As the sun ages, even microscopic variations in core temperature produce notable effects on how efficiently hydrogen nuclei overcome their natural repulsion and fuse. When the temperature rises slightly due to the gradually increasing density of the helium core, it boosts the fusion rate just enough to increase the sun's total energy output, still by margins too small for ancient humanity to sense. These early luminosity changes ripple outward through the sun's layered interior, traveling as photon energy that takes hundreds of thousands of years to escape from the radiation zone, slowly adjusting the brightness emitted by the photosphere. Although the sun appears constant from Earth, with its radiance unwavering, astrophysicists know that these internal transformations represent the earliest stages of a long evolutionary arc that will one day reshape the entire structure of the solar system. Even the sun's magnetic field feels the influence of these small shifts, though the connection is complicated and spans vast stretches of time. As the core gradually heats and fusion becomes marginally more vigorous, the convective zone experiences slight changes in its flow patterns. These convection adjustments alter the sun's magnetic dynamo cycle, though the effects are so subtle they manifest only in statistical trends across thousands or millions of years. The familiar 11-year solar cycle, marked by sunspots, flares, and magnetic polarity flips, continues as usual, but beneath this pattern lies a slowly evolving baseline shaped by deep core physics. Scientists suspect that these near-invisible alterations are part of why the sun's magnetic activity has not remained perfectly uniform throughout its history, instead exhibiting eras of unusually high or low activity, such as the Maunder minimum. Inside the sun's core, the buildup of helium continues relentlessly, even though the sun has only consumed roughly half of its hydrogen fuel after 4.6 billion years. This accumulation changes the mean molecular weight of the plasma, increasing the density and requiring slightly higher internal pressure to maintain equilibrium against gravitational collapse. These shifts are minuscule, progressing so gradually that if one could somehow pause time every 100,000 years and compare the sun to its previous state, the differences would seem almost laughably small. Yet nature's patience is infinite, and over immense stretches of cosmic time, these incremental changes compound, pushing the Sun toward inevitabilities that will eventually break the delicate balance it has maintained for billions of years. Over time, the luminosity of the Sun has already increased by about 30% since it first formed, a significant change, though it happened over such a long period that life on Earth adapted as the environment evolved. In the current era, the ongoing increase is still occurring, though at a slow pace, caused not by any sudden outburst but by these tiny core temperature adjustments. These luminosity increases alter the solar constant, the amount of sunlight reaching Earth, which affects everything from planetary climate to atmospheric chemistry. Future Earth will grow warmer not because of surface solar events, but because of the Sun's slow march toward greater energy production. Aleoseismology, the study of pressure waves traveling through the Sun, reveals the fine-grained structure of these early internal shifts. Sound waves move differently when the density or temperature of the core changes, and by analyzing oscillations, scientists can map the Sun's inner layers much like seismologists map Earth's interior. These measurements confirm that the Sun's core is gradually evolving, with slight modifications in sound speed profiles indicating ongoing structural readjustments tied to rising temperature and density. These findings support theoretical models predicting the Sun's slow brightening and tightening core. Even the balance between radiation pressure and gravity shifts subtly as the core warms. A hotter core produces more radiation, exerting stronger outward pressure, which counters gravity more efficiently. The result is a delicate expansion in the outer layers, not enough for the Sun to appear larger in any noticeable way, but sufficient to produce measurable differences in stellar models. This gentle inflation serves as a precursor to the more dramatic swelling the Sun will undergo billions of years later, long after these early signs have compounded into larger-scale structural transformations. The Sun's energy flow, photons slowly migrating outward from the core, also shifts in response to these internal temperature fluctuations. The opacity of the Sun's plasma varies with temperature and composition. As helium becomes more abundant, it subtly alters how efficiently radiation can move through the star's interior. These opacity changes can lead to slightly altered photon paths, affecting how quickly energy escapes. Over enormous timescales, this interplay between opacity and fusion rate becomes one of the key drivers of the Sun's evolving luminosity profile. The small luminosity changes radiating from the photosphere also influence the solar wind, the stream of charged particles flowing outward into the solar system. Even slight variations in magnetic activity and surface temperature can alter the intensity and composition of the solar wind, though these effects are mild during this early evolutionary stage. Over vast periods, however, they contribute to the long-term shaping of planetary atmospheres, including the gradual erosion of Mars's once thicker atmosphere. All these subtle shifts, occurring over tens of thousands to millions of years, shape the Sun's long-term stability. A star like the Sun is a dynamic system perpetually seeking equilibrium. Gravity pulls inward, fusion pressure pushes outward, and the slightest imbalance triggers compensatory changes. These early phase shifts reflect the Sun's ongoing effort to maintain this equilibrium as the raw material of fusion slowly diminishes in the core. Each tiny rise in temperature or energy output is the Sun's response to the gradual transformation of its fuel supply. In essence, the Sun is slowly adjusting itself to its own aging process, long before any dramatic expansion or red giant phases begin. These internal recalibrations are quiet, invisible, and steady, yet they are the opening movements of a vast stellar evolution cycle that will eventually reshape the entire solar system. Even the faint increase in luminosity affects Earth's long-term habitability, subtly nudging climate patterns in ways that only become prominent far in the future. As the Sun continues to age, these early shifts establish the framework for later evolutionary phases. The increasing core temperature does not simply enhance fusion, it slowly sets the stage for a runaway process that will ultimately lead to the Sun exhausting its hydrogen in the core. Once this occurs, the Sun will begin fusing hydrogen in a shell around the core, triggering the dramatic expansion associated with the red giant phase. But long before those transformations, these nearly invisible adjustments mark the Sun's quiet progression toward that distant future. Meanwhile, the Sun's internal rotation profile also changes. The core rotates faster than the outer layers, and as the internal structure gradually shifts, so does the coupling between these regions. Over millions of years, this rotational decoupling subtly alters magnetic field generation dynamics. Again, the effects are not immediate or obvious, but they represent deep structural adjustments driven by long-term evolution rather than short-term solar cycles. Another consequence of rising core temperature is a slight increase in neutrino production. Neutrinos, produced in fusion reactions, pass through matter nearly unhindered, providing a direct glimpse into the Sun's core processes. As the fusion rate gradually increases, so does the Sun's neutrino output, offering scientists another way to detect these subtle shifts. Long-term neutrino observations confirm that the Sun's fusion rate is not static but evolves in accordance with theoretical predictions. Over time, even the chemical stratification of the Sun changes. Helium produced in the core stays there because convection does not reach deep enough to mix the Sun's composition thoroughly. This leads to a growing helium-rich core surrounded by hydrogen layers, creating sharper gradients in density and temperature. These gradients influence everything from the Sun's oscillation patterns to the efficiency of energy transport. As these internal gradients sharpen, they also affect the stability of the solar interior. Certain layers become more prone to instabilities that influence the flow of energy and magnetic fields. These instabilities are extremely mild at this early stage but are harbingers of the more pronounced internal turbulence that will emerge in later phases of the Sun's evolution when hydrogen becomes scarce in the core. Over hundreds of millions of years, these early adjustments in brightness will have consequences for Earth's climate and biosphere. Even a small increase in total solar irradiance warms the planet's surface, altering weather patterns, ocean circulation, and the long-term carbon cycle. Although such changes are gradual, they contribute to the slow march toward a hotter future Earth, long before the red giant era begins. Energy transport through the Sun's outer convective zone also shifts as the internal structure evolves. Slight changes in temperature alter the size and efficiency of convection cells, subtly modifying the granulation patterns visible on the Sun's surface. These changes remain too small for most observers to detect, but are quantifiable through sensitive instruments and long-term solar studies. Finally, these subtle early shifts represent the Sun's preparation for its eventual transformation. The Sun is not a static ball of gas but a living, evolving system shaped by nuclear processes, gravity, and thermal dynamics. Each minor fluctuation in temperature, luminosity, or density is part of a long chain of events that will someday lead the Sun to swell, brighten dramatically, shed its outer layers, and leave behind a white dwarf. What begins with tiny internal adjustments will end with the remaking of the solar system. Explain how. These small solar changes could translate into noticeable, long-term climate shifts on Earth and other planets. Even the slightest increase in the Sun's luminosity can reshape a planet's climate over geological timescales, because climate is a cumulative system that responds to persistent forcing rather than immediate shocks. A fractional rise in the amount of solar energy Earth receives may seem insignificant on a year-to-year basis, but across tens of thousands or millions of years, this small shift adds up, amplifying feedback loops within Earth's atmosphere and oceans. The result is a slow warming trend that may start imperceptibly, gradually nudging average global temperatures upward, subtly altering precipitation patterns, and shifting climate zones toward the poles. These early modifications represent the initial stages of a far larger evolutionary arc driven by the Sun's growing brightness as it ages. As Earth absorbs slightly more solar energy, the planet's delicate radiative balance shifts. The incoming radiation from the Sun begins to exceed the outgoing heat Earth can radiate back into space, even if only by a small margin. This tiny imbalance is enough to warm the lower atmosphere, which increases the capacity of air to hold water vapor, a greenhouse gas far more potent than CO in terms of sheer radiative impact. Over time, this additional water vapor amplifies warming further, creating a gradual but accelerating feedback loop. This process is one reason climatologists believe Earth's long-term climate trajectory is inherently tied to the Sun's evolution, regardless of shorter-term variations caused by natural cycles or human activity. Marine environments also feel the influence of these subtle solar changes. Because oceans store vast amounts of heat, they respond slowly, meaning that even minor increases in solar irradiance are absorbed and retained over long durations. Warmed ocean surfaces evaporate more readily, increasing global humidity and cloud formation, which can alter albedo and precipitation patterns. Some regions may become wetter, others drier, all governed by shifting circulation patterns driven by thermal gradients. Ocean currents, which regulate climate by transporting heat around the globe, may adjust their strength or direction over immense timescales as a result of this incremental solar warming. Continents experience changes as well, as higher temperatures influence soil moisture, vegetation distribution, and the reflectivity of Earth's surface. Over millions of years, these solar-driven climate shifts could transform entire ecosystems, causing tropical zones to expand, temperate regions to shift poleward, and deserts to grow or shrink depending on how precipitation patterns evolve. These long-term climatic migrations are tied directly to the Sun's gradual brightening throughout its main sequence life, demonstrating how seemingly tiny internal solar changes have far-reaching planetary consequences. Even the cryosphere, the frozen portions of Earth, responds over immense timescales to subtle increases in solar output. Slightly warmer summers lead to marginally faster melting of glacier and polar ice sheets, altering sea levels and freshwater distribution. Though these changes occur slowly on the scale of millennia, their cumulative effect reshapes coastlines, alters habitats, and modifies ocean temperatures by diluting seawater with meltwater. This process plays a major role in long-term climate cycles and contributes to how Earth transitions between glacial and interglacial periods. These early solar-driven changes also interact with Earth's carbon cycle. Warmer oceans absorb less carbon dioxide, allowing more of it to remain in the atmosphere, which intensifies greenhouse warming. Likewise, soil processes and biological activity shift with rising temperatures, sometimes accelerating carbon release or altering the balance of major carbon sinks. These slow adjustments may set Earth on a path toward a progressively warmer climate over tens of millions of years, reducing the planet's ability to regulate temperature through natural feedbacks. Earth's atmosphere isn't the only one influenced by subtle changes in solar output. Mars, for instance, with its thin atmosphere and low capacity to buffer temperature changes, is even more susceptible to small variations in solar irradiance. A slight rise in the Sun's brightness warms the Martian surface enough to spark more frequent or intense dust storms, which redistribute heat across the planet in ways that amplify regional temperature swings. The sublimation of carbon dioxide from the polar caps may also increase during warmer periods, temporarily thickening the atmosphere, a small effect, but significant on a world where climate responses are inherently sensitive. Venus, already locked in a runaway greenhouse effect, is influenced differently by subtle solar changes. Even a slight increase in solar luminosity enhances the extreme greenhouse environment, raising surface temperatures further and altering atmospheric dynamics. Over long timescales, these changes can modify wind patterns, cloud layers, and the distribution of reflective aerosols in Venus's hostile atmosphere. Though the planet is already intensely heated, small solar variations still add measurable forcing to a system prone to extreme stability and extreme change simultaneously. Gas giants also respond, though their enormous atmospheres buffer changes more effectively. Jupiter and Saturn may experience long-term shifts in cloud structures, atmospheric chemistry, or storm activity as solar input changes slightly. Even though they are far from the Sun, their upper atmospheres are sensitive to total incoming radiation and the solar wind, meaning that subtle solar evolution affects auroras, atmospheric heating, and upper layer dynamics across millions of years. These changes illustrate that no planet in the solar system is completely isolated from the Sun's slow transformation. Earth's long-term habitability window is strongly influenced by the Sun's steady brightening. Even small increases in solar output, compounded over geologic timescales, gradually push the planet toward a threshold where carbon dioxide levels must drop to maintain climate stability. Over time, Earth's natural carbon sequestration processes may struggle to reduce CO fast enough to counteract increased heating, eventually leading to a climatic tipping point. Long before the Sun reaches its red giant phase, Earth may undergo a moist greenhouse state triggered by these subtle yet persistent increases in solar luminosity. Another key factor is how these small solar changes influence Earth's orbital climate cycles. Over hundreds of thousands of years, Milankovitch cycles, variations in Earth's orbit and axial tilt, interact with solar luminosity fluctuations. When natural orbital warming coincides with even slightly higher solar output, glacial periods end more abruptly or interglacial periods last longer. Conversely, orbital cooling may not fully counteract the Sun's gradual brightening, leading to long-term warming trends despite periodic dips in global temperature due to orbital geometry. Because the Sun's luminosity increases slowly, the climate's response is often non-linear. Small changes in forcing can lead to significant transitions, such as shifts in monsoon patterns, reorganization of jet streams, or long-term transformations in atmospheric circulation. These shifts may appear minor at first but accumulate into profound climate rearrangements that alter ecosystems, sea levels, and continental weather patterns across tens of thousands of years. These subtle shifts also contribute to long-term changes in Earth's hydrological cycle. As solar energy input increases, evaporation intensifies globally, leading to heightened atmospheric moisture content. This increased moisture enhances rainfall in some regions while causing drought in others, depending on how large-scale circulation patterns redistribute heat and water vapor. Over millions of years, this can drastically reshape river systems, groundwater distribution, and regional stability of lakes and inland seas. Even biological evolution responds to solar-driven climate changes. Organisms must adapt to shifting temperature zones, evolving traits that suit gradually warming environments. Species distribution patterns drift poleward, biodiversity hotspots migrate, and ecosystems transform as solar input slowly rises. These evolutionary pressures reflect the deep connection between solar evolution and planetary biospheres, a relationship that has shaped life for billions of years and continues to do so even through the smallest changes. Over still longer timescales, as the Sun continues increasing in luminosity, Earth's climate may surpass key tipping points such as the loss of low-latitude cloud cover. This would dramatically intensify solar heating at the surface, accelerating the progression toward a more hostile climate. Even this outcome begins with almost undetectable solar changes, demonstrating how delicate Earth's climate system is when stretched across millions of years of solar evolution. Solar-driven variations also influence planetary magnetic environments. Changes in solar wind intensity and particle output affect Earth's magnetosphere, which helps shield the planet from high-energy radiation. Even slight increases in solar activity can modify the shape and strength of this shield over long intervals, subtly altering the amount of charged particles that reach the upper atmosphere. Over millions of years, this may impact atmospheric retention and chemical processes. On planets without strong magnetic fields, such as Mars, these solar wind changes affect atmospheric erosion rates. Slight increases of solar wind intensity tied to internal solar evolution can accelerate the loss of atmospheric particles, slowly thinning an already fragile atmosphere. This makes Mars increasingly susceptible to climate extremes and contributes to its long-term transition toward a colder, drier state. Even ring systems around gas giants may be influenced over enormous timescales, as changing solar radiation subtly alters electrostatic forces, dust movement, and ring chemistry. While these changes are far less dramatic than those on terrestrial planets, they reflect an important truth. The Sun's evolution radiates outward as a universal influence, quietly reshaping every object in its gravitational domain. As climate systems respond, feedbacks on all planets become more pronounced. Some amplify warming, others counteract it, but all of them interact with the Sun's slow evolution. These feedbacks ensure that even tiny changes in solar output cannot simply fade into the background. They become woven into the long-term story of planetary transformation. Ultimately, the Sun's slow brightening is a gentle but relentless force, shaping climates across the solar system in ways that accumulate over vast spans of time. What begins as minute changes in the Sun's core temperature and luminosity eventually manifests as sweeping transformations in planetary environments and histories. Even the smallest solar shifts, repeated and sustained across millions of years, become powerful agents of change on every world orbiting our star. Discuss the potential for increased solar flare activity or coronal mass ejections impacting technology and infrastructure. As the Sun undergoes subtle internal shifts that gradually enhance its luminosity and alter the dynamics within the convection zone, the magnetic activity that drives solar flares and coronal mass ejections, CMEs, may also intensify over extremely long timescales. While these changes are not abrupt, the delicate interplay between convection, differential rotation, and the solar magnetic dynamo suggests that even small adjustments deep within the Sun can influence the frequency and magnitude of magnetic eruptions. These eruptions, manifesting as bursts of high-energy particles, intense radiation, and massive plasma clouds hurled into space, pose significant risks to modern technological systems, many of which are highly sensitive to disturbances in the electromagnetic environment. Increased solar activity means that Earth's magnetosphere would be confronted more frequently with high-speed solar wind streams and energetic particle storms. When a CME hits Earth, it compresses the magnetosphere, forcing charged particles into the upper atmosphere and dramatically increasing geomagnetic currents. These interactions can disrupt radio communications, degrade GPS accuracy, and introduce noise into satellite systems that rely on precise timing signals. Even slight increases in flare intensity can temporarily disturb the ionosphere, causing unpredictable changes in signal propagation that interfere with aircraft navigation and long-range communication systems. The technological world of today is far more vulnerable to solar storms than humanity was even a century ago. Many systems, from electrical grids to satellite constellations, have become deeply interconnected and reliant on stable electromagnetic conditions. During intense geomagnetic storms, powerful currents can flow through long electrical transmission lines, overloading transformers and damaging components that are expensive and difficult to replace. Even minor increases in the Sun's magnetic volatility over thousands of years could create a long-term pattern of more frequent disruptions, punctuated by rare but catastrophic events reminiscent of the historical Carrington event of 1859. In the modern era, a Carrington-level solar storm would be devastating. Satellites could be partially or completely disabled, losing their ability to provide essential services like telecommunications, weather monitoring, and global navigation. Spacecraft electronics may be exposed to dangerous radiation, overwhelming shielding and causing system failures. Astronauts in orbit or traveling beyond Earth's protective magnetic field would face heightened exposure to particle radiation, potentially reaching lethal levels without specialized shelters. These threats become more pressing if solar activity slowly increases over time. Even routine solar flare activity affects the reliability of power systems. Transformers cause heat more during geomagnetic disturbances due to induced currents, and over decades of repeated exposure, this additional thermal stress can weaken the insulation materials, increasing the risk of failures. If solar flare activity becomes more frequent even by a modest fraction, the cumulative effect on global energy infrastructure could be significant. Large transformer failures are especially worrisome because they are not easily replaced. Manufacturing new ones often requires months or years, and global supply chains are ill-prepared for widespread demand caused by a large solar event. A long-term trend toward increased solar volatility could also influence aviation. High-altitude flights near the poles, which rely heavily on satellite communications and GPS, face greater risks from heightened radiation and ionospheric disturbance. Airlines may be forced to divert flights away from polar routes more often during solar storms, increasing flight times, fuel consumption, and operational costs. Over centuries, even minor incremental increases in flare activity could significantly reshape the logistical strategies of global air travel. Space-based technology, such as the rapidly growing networks of communication and observation satellites, is particularly vulnerable to solar storms. The low Earth orbit environment becomes more hostile during periods of increased solar activity because solar heating expands the upper atmosphere, increasing atmospheric drag. Satellites experience greater friction, causing them to lose altitude faster and requiring more frequent orbital corrections. In extreme cases, satellites may re-enter the atmosphere prematurely. With thousands of satellites now populating Earth's orbit, enhanced solar activity poses a serious risk to orbital traffic, satellite lifespans, and the future of space infrastructure. Navigation systems are also sensitive to solar disturbances. GPS signals, which depend on precise timing and travel through the ionosphere, can experience delays and degradation during solar flare events. These disruptions may cause navigation errors for civilian and military systems, impacting everything from maritime operations to automated drones. Over long intervals, if solar flare intensity shifts upward, it would force technological adaptation and redundancy planning to ensure continued functionality under harsher solar conditions. Additionally, increased solar flare activity enhances radiation exposure for passengers on high-altitude flights. During major events, radiation levels at cruising altitudes can spike significantly, posing health risks to frequent flyers and aircrew, especially on polar routes where Earth's magnetic shielding is weaker. If these events become even slightly more common across millennia of solar evolution, aviation regulations may eventually change to account for increased exposure risks. Telecommunications infrastructure, particularly undersea cables and long-distance fiber optic lines, is not immune to solar interference. While optical fibers themselves are not conductive, the repeaters and power systems that support these networks are susceptible to geomagnetically induced currents. A strong solar storm can damage these components, disrupting global internet connectivity. As human dependence on digital communication deepens, even small increases in the frequency of damaging solar events could create cascading failures that affect economies worldwide. The growing space economy, reliant on satellite networks, crewed missions, lunar operations, and eventual Mars expeditions, faces additional vulnerabilities. Spacecraft traveling between planets are directly exposed to high-energy particles from solar flares. Without robust shielding and predictive capabilities, astronauts could be endangered by sudden solar particle events. If internal solar changes subtly raise the likelihood of such eruptions over future millennia, human deep space exploration strategies will need to evolve accordingly. Ground-based technologies such as pipelines are also unexpectedly vulnerable. Geomagnetic storms can induce electric currents in long metal structures, accelerating corrosion and increasing the risk of leaks or failures. These effects accumulate over time, so a slight long-term increase in solar activity could shorten the lifespan of critical infrastructure and raise maintenance costs globally. Moreover, the increased radiation associated with intensified solar events can affect the performance of semiconductor devices. High-energy particles can penetrate microchips and cause single-event upsets, momentary glitches that can crash systems, corrupt data, or disable electronics. As global infrastructure becomes more automated and reliant on complex electronics, the cumulative effect of heightened solar radiation could pose systemic risks to safety-critical technologies. Agricultural systems may also feel indirect effects. Satellite imagery, GPS-guided farming equipment, and climate monitoring technologies depend on stable electromagnetic conditions. Disruptions caused by solar storms could interfere with the data farmers use to optimize planting, irrigation, and harvest timing. Over time, even minor shifts in solar activity patterns could force adaptations in agricultural planning. Increased solar flare activity also challenges global power grids by destabilizing frequencies and voltages. Grid operators must react quickly during geomagnetic disturbances, sometimes taking sections of the grid offline to avoid permanent damage. As solar activity becomes more erratic over long timescales, these interventions would need to happen more frequently, complicating energy distribution and reliability. There is also concern about the cumulative economic impact. Even mild solar events can cost millions in disrupted operations, rerouted flights, or satellite corrections. A long-term upward trend in solar magnetic volatility could drive the need for costly infrastructure upgrades, hardened electronics, improved forecasting systems, and expanded shielding for spacecraft and power networks. Space weather forecasting would become increasingly critical. With more frequent flares and CMEs, predicting solar storms accurately would be essential to protect satellites, astronauts, and power grids. Agencies around the world would likely invest heavily in early warning systems, solar observatories, and heliophysics research to mitigate the growing risks associated with heightened solar activity. For Earth's magnetosphere, increased solar flare activity means more intense and frequent geomagnetic storms, which in turn may reshape the dynamics of the radiation belts. These belts trap charged particles, and during heightened solar activity, they can swell, intensifying radiation hazards for satellites and spacecraft. Over centuries, a more active radiation environment would require fortified satellite designs and safer orbital strategies. Other planets, too, would feel the effects. Mars, with its weak magnetic field, would experience increased atmospheric loss during solar storms, accelerating long-term trends toward a thinner atmosphere. Jupiter's magnetosphere would capture larger quantities of solar particles, enhancing auroral activity but also exposing moons like Europa and Ganymede to increased radiation. These effects highlight the solar system's wide reach of even moderate changes in the Sun's magnetic behavior. Ultimately, the potential for increased solar flare activity underscores the vulnerability of technological civilization to a star that remains dynamic and evolving. While humanity has built a world deeply dependent on electronics, satellites, and power grids, the Sun's long-term magnetic fluctuations are beyond human control. As its internal structure slowly shifts over millions of years, the impact on solar activity may reshape the technological landscape repeatedly, forcing continuous adaptation and innovation. Explore how the Sun's gradual evolution might affect the orbital stability or atmospheric composition of inner planets like Venus and Mercury. As the Sun ages and slowly increases in luminosity, the inner planets will face a progressive intensification of solar radiation that alters not only their thermal environments but also their orbital and atmospheric dynamics. Mercury and Venus, already residing in regions of extreme solar influence, are particularly vulnerable to subtle but cumulative changes in solar output. Over millions and billions of years, even slight increases in the Sun's energy output translate into significant modifications in how these planets interact with solar gravity, radiation pressure, and the solar wind, setting the stage for transformations that differ dramatically from those expected for more distant worlds. Mercury, being the closest to the Sun, experiences the most immediate consequences of solar evolution. Its orbit is already shaped by the Sun's gravitational pull, but the long-term brightening and mass loss from the Sun alter that relationship. As the Sun gradually sheds mass through the solar wind and nuclear fusion processes, Mercury's orbit will slowly expand. Although this expansion occurs at an almost imperceptible rate over billions of years, the cumulative effect can change Mercury's orbital parameters, influencing its eccentricity and potentially making its already elongated orbit even more stretched. This subtle orbital drifting, when combined with solar tidal forces, may lead to complex gravitational interactions that redefine the planet's long-term orbital fate. In addition, Mercury's rotation, which is locked in a 3:2 spin orbit resonance with the Sun, may become increasingly unstable as the Sun evolves. Changes in the distribution of solar radiation over time can deepen tidal stresses on Mercury's crust and mantle. While these stresses do not produce dramatic tectonic events like those on Earth, they do influence the internal structure and thermal evolution of the planet. Over long periods, even small tidal adjustments can shift the planet's rotational alignment, modify surface stress patterns, and affect the rate at which its interior cools. The solar wind also plays a key role in shaping Mercury's tenuous exosphere, which is composed of atoms knocked off its surface by radiation and micrometeoroid impacts. As the Sun slowly intensifies, the flux of solar wind particles increases, enhancing sputtering and stripping more atoms from Mercury's surface. This results in a dynamic exosphere that becomes increasingly dominated by solar-driven processes. Over geological timescales, Mercury's surface may become more heavily altered by these interactions, potentially leading to a gradual thinning of volatile elements and a change in the chemical makeup of the exosphere. The thermal environment on Mercury will also worsen as the Sun grows brighter. With its weak atmosphere and slow rotation, Mercury already experiences dramatic temperature swings between day and night. Over time, higher solar irradiance will push daytime temperatures to even more extreme levels, perhaps leading to surface changes such as enhanced space weathering or the possible alteration of minerals through repeated cycles of heating and cooling. These shifts may subtly erode Mercury's landscape, changing the reflectivity of its surface and influencing how it absorbs solar energy. Venus, though farther from the Sun than Mercury, faces equally profound evolutionary pressures because of its dense atmosphere and unique greenhouse conditions. As the Sun brightens, Venus will absorb increasing amounts of solar energy, further amplifying its already runaway greenhouse effect. The result is an even hotter, more hostile surface environment where the thick carbon dioxide atmosphere traps additional heat, driving surface temperatures higher and intensifying atmospheric superrotation. This energy boost may accelerate the chemical reactions that dominate Venus's atmospheric chemistry, leading to a greater buildup of greenhouse gases or the destruction of particular compounds. The high-altitude cloud layers of Venus, composed of sulfuric acid droplets, will also be affected. Increased ultraviolet radiation from the evolving Sun would accelerate photochemical reactions, altering the chemical pathways that maintain the cloud layers. This could change the vertical distribution of aerosols, influence the planet's albedo, and potentially modify the reflective properties that regulate how much sunlight reaches the lower atmosphere. Over hundreds of millions of years, these changes could significantly reshape Venus's climate system. Solar evolution may also impact Venus's atmospheric escape rates. As the Sun emits more energetic photons and a stronger solar wind, the upper atmosphere of Venus becomes more vulnerable to stripping. Although Venus lacks a protective magnetic field, its dense atmosphere shields the lower layers from immediate loss. However, the upper layers, particularly hydrogen atoms from water vapor, are continually eroded by the solar wind. A more energetic sun accelerates this process, contributing to the long-term dehydration of the planet. The result is a continued loss of water-related species and a shift toward an even drier, more oxidized atmospheric composition. Orbital stability is another factor for Venus. Like Mercury, Venus will experience subtle outward migration as the Sun loses mass. While the orbital shift is small, its interaction with the planet's dense atmosphere and internal dynamics could play a role in determining how the planet's rotation evolves across long periods. Venus's slow retrograde rotation makes it particularly sensitive to solar tides. With the Sun growing brighter, these tidal forces may gradually alter its rotational speed or axial tilt, contributing to long-term atmospheric reorganization. The interplay between solar radiation and Venus's atmosphere also influences surface conditions indirectly. As the Sun brightens, volcanic outgassing, if still active, may become more influential, as additional heat could influence mantle convection patterns. Although Venus does not possess plate tectonics, plume-driven volcanic activity may respond to slight thermal changes over geological timescales. Increased volcanic eruptions would inject more sulfur dioxide into the atmosphere, intensifying cloud formation and modifying Venus's greenhouse strength. This creates a feedback cycle in which solar-driven heating interacts with internal geologic activity. Mercury's long-term orbital stability becomes particularly interesting when considering gravitational interactions with Venus and Earth. As solar mass loss gradually pushes planetary orbits outward, resonance conditions could shift subtly. These changes might introduce periods of mild orbital instability for Mercury, potentially increasing its eccentricity or slightly altering orbital inclination. Although doomsday scenarios of Mercury colliding with Venus or falling into the Sun are extremely unlikely, the gravitational interactions become more dynamic as the Sun evolves, forcing Mercury's orbit to adjust to new resonance configurations. Similarly, Venus's orbital evolution may influence the stability of its atmosphere. A slight outward migration reduces the solar flux Venus receives, but not enough to counteract the Sun's increasing luminosity. Instead, this migration subtly affects atmospheric circulation patterns and the distribution of heat across the planet's surface. Over long periods, the interplay between orbital drift and solar brightening shapes a new equilibrium that continues to favor extreme greenhouse conditions but may produce distinct atmospheric layers or altered cloud structures. Another important aspect of the Sun's evolution is the impact of increased ultraviolet and X-ray radiation on both planets. These high-energy photons drive ionization processes in the upper atmospheres of Mercury and Venus. On Mercury, this means stronger surface-bound exospheric processes and greater variability in the chemical composition of its near-surface environment. On Venus, the ionosphere becomes more active, with greater electron densities leading to stronger interactions with the solar wind. This enhanced coupling can alter the bow-shock region around Venus and increase the rate of atmospheric loss over vast spans of time. The long-term fate of Mercury's surface is also shaped by the Sun's intensifying heat. At extremely high temperatures far into the future, certain minerals may begin to melt or undergo chemical transformation. Repeated cycles of intense solar exposure could gradually alter the regolith, changing its reflectivity and thermal properties. This creates a slow feedback loop in which Mercury absorbs more solar energy, further raising surface temperatures and enhancing the rate of surface alteration. For Venus, the deeper atmosphere also evolves. High temperatures and increased solar input may push the already dense atmosphere toward even greater pressure and thermal gradients. While Venus is unlikely to lose enough atmosphere to cool significantly, the composition may change in ways that influence long-term chemical pathways. For instance, increased thermal energy may break down more carbon dioxide molecules in the upper atmosphere, leading to shifts in the balance between CO and other trace gases. Over millions of years, these shifts could subtly alter the greenhouse structure of the atmosphere, creating a new equilibrium state. In addition, both planets respond differently to long-term solar mass loss. As the Sun loses mass, its gravitational grip weakens slightly. Mercury, being closest, experiences the greatest fractional change in gravitational binding. Over immense timescales, this may contribute to slow orbital drift that interacts with tidal forces to influence Mercury's rotation. Venus also feels this gravitational weakening, though to a lesser extent. The combined effect of mass loss and increasing solar radiation shapes the long-term orbital architecture of the inner solar system. The increased solar radiation environment also intensifies space weathering across both planets. On Mercury, enhanced bombardment by charged particles and micrometeorites, accelerated by the Sun's changing radiation pressure, modifies the surface regolith, creating a darker, more mature layer over time. This affects the planet's albedo and thermal inertia. Venus, although shielded by its thick atmosphere, experiences atmospheric erosion and chemical modification in its upper layers, driven by stronger solar particle events and more intense ionization. Furthermore, Venus's thick clouds respond dynamically to small increases in solar input. Higher temperatures increase the evaporation of sulfuric acid droplets in some regions, while other regions may see enhanced condensation. These changes alter cloud opacity and thickness, influencing both the scattering of sunlight and the trapping of infrared radiation. The shifting distribution of cloud layers may produce long-term oscillations or cycles in Venusian weather patterns driven by the Sun's evolution. Mercury's magnetosphere, weak and transient as it is, also interacts differently with a more active Sunday. Stronger solar wind pressures compress Mercury's magnetosphere to a greater extent, increasing the direct interaction between solar wind particles and the planet's surface. This intensifies sputtering processes and may gradually alter the surface composition. Over time, Mercury's surface could become even more iron-rich as lighter elements are stripped away more efficiently. Even Venus's slow rotation, which contributes to its extreme atmospheric dynamics, may be influenced by solar tides strengthened by the Sun's brightening. Over long periods, these tides could subtly modify Venus's rotational period, potentially slowing it further or introducing variations in atmospheric superrotation. These shifts reshape the long-term climate equilibrium on Venus, especially in the upper atmosphere where tidal effects are more pronounced. Ultimately, the Sun's gradual evolution is a driving force behind the long-term destinies of Mercury and Venus. Though the changes occur over timescales far beyond human experience, they reflect an inexorable process in which the inner planets are gradually reshaped by the increasing power and evolving nature of the star they orbit. Mercury becomes hotter, more eroded, and more gravitationally unbound, while Venus becomes an even more intense greenhouse world with shifting atmospheric chemistry and altered orbital dynamics. These transformations illustrate the profound influence that even subtle solar evolution can exert across billions of years. Consider the ripple effects on the outer solar system, such as changes in the Kuiper belt or Oort cloud. As the Sun continues its slow, predictable evolutionary path, its influence does not end with the inner planets or the region of the asteroid belt. Far beyond the familiar orbits of Jupiter and Saturn, subtle changes in solar output can propagate outward, affecting regions that seem too distant to notice any shift. Yet even a tiny variation in solar gravity, radiation pressure, or magnetic field strength can accumulate over millions of years, nudging entire populations of icy bodies in ways that reshape the outskirts of our cosmic neighborhood. These distant zones, the Kuiper belt and the Oort cloud, are highly sensitive to long-term perturbations, and variations in the Sun's life cycle can alter their structure more profoundly than most imagine, creating a slow, cascading reaction that redefines the distribution of comets, dwarf planets, and primordial debris. As solar luminosity subtly increases over geological timescales, the energy reaching the Kuiper belt may rise just enough to affect the delicate equilibrium governing the surfaces of its icy worlds. Although these bodies remain far below the freezing point of most substances, additional energy can drive enhanced sublimation of volatile ices such as nitrogen and methane. The process is extraordinarily slow but persistent, gradually reshaping surface geology and potentially altering the thin, transient atmospheres of larger objects like Pluto or Eris. These microchanges in energy input can also influence the chemical evolution of their surfaces, promoting reactions that darken or brighten them over millions of years, leading to shifts in their reflectivity and thermal behavior that compound the changes introduced by rising solar output. Over extended periods, the Sun's evolving magnetic field exerts a quiet but powerful influence on the behavior of charged particles streaming through the solar system. In the inner regions, the heliospheric boundary expands and contracts, but its outer reach determines how effectively the Sun shields the Kuiper belt and Oort cloud from galactic cosmic rays. As the Sun ages, its magnetic shield weakens, allowing more high-energy particles to permeate the distant zones. This influx can initiate chemical transformations on the surfaces of icy bodies, producing organic compounds and altering their spectral signatures. A shift in cosmic ray exposure over millions of years can profoundly impact the composition of these ancient objects, leaving a record of solar evolution etched into their frozen crusts. The gradual increase in the Sun's mass loss rate, particularly during its later stages, can produce a noticeable reduction in gravitational binding across the solar system. When the Sun sheds mass through enhanced stellar winds, even at a slow pace, the gravitational pull on distant objects weakens. While the inner planets might only adjust their orbits slightly, the Kuiper belt, already a region of marginal orbital stability, may experience dramatic consequences. Orbits elongate, resonances break, and previously stable bodies may drift into trajectories that send them inward as long-period comets or outward into interstellar space. These changes unfold gradually but relentlessly, causing the architecture of the Kuiper belt to expand and diffuse over eons. As the heliosphere inflates or contracts in response to solar activity, the boundary that protects the solar system from interstellar material subtly shifts. This movement influences how interstellar gas and dust interact with the Oort cloud, which stretches tens of thousands of astronomical units from the Sun. Variations in the shape or strength of the heliosphere can expose different pockets of the Oort cloud to external pressure, leading to redistributions of cometary bodies. Some may be nudged inward toward the Sun, feeding long-term increases in comet influx toward the inner solar system, while others are pushed outward, where they risk being stripped away by passing stars or the galactic tide. The Sun's future transition into a brighter and more expanded star during its red giant phase will send ripples through the Kuiper belt long before it physically interacts with the region. Even slight increases in radiation and solar wind intensity can alter the thermal structure of large Kuiper belt objects, potentially awakening internal processes that have been dormant for billions of years. Sublimation-driven jets might become more active, reshaping surface features and causing rotational changes that affect orbital stability. These effects are subtle on short timescales but profound when viewed across millions of years, illustrating how distant icy worlds remain responsive to the Sun's evolving energy output. The influence of a gradually changing Sun extends to the gravitational tapestry of the solar system. As solar mass decreases over time, gravitational resonances that currently maintain order in the Kuiper belt may weaken or dissolve entirely. Regions once stabilized by Neptune's gravitational pull could lose their structure, allowing objects to migrate chaotically. This could empty some zones while filling others, creating a shifting population of bodies that mirror the Sun's long-term evolution. The breakdown of resonant chains may even release objects that have remained trapped for billions of years, sending them on new orbital journeys that were previously impossible. Even small changes in radiation pressure can accumulate across astronomical distances, altering the delicate balance that governs dust and microparticle populations in the Kuiper belt. As solar radiation increases, these fine particles may be pushed outward more aggressively, decreasing their density near the inner edge of the belt. This long-term clearing effect could affect collisional rates among larger bodies by reducing the amount of debris available to influence orbital evolution. Over millions of years, such a shift can create new patterns of impact histories and surface morphologies, subtly rewriting the geological timelines of Kuiper belt objects. In the Oort cloud, the sheer scale of its population, trillions of icy bodies, means even minimal solar changes produce systemic effects. As the Sun loses mass and its gravitational influence diminishes, the binding energy holding Oort cloud objects in place weakens. Many of these distant bodies hover on the edge of interstellar escape velocity, so even slight changes can push them beyond the solar system entirely. The Oort cloud gradually thins, turning from a vast spherical reservoir into a more diffuse halo. Over the Sun's lifetime, this gradual thinning may reduce the frequency of new long-period comets entering the inner solar system. The interplay between interstellar medium pressure and solar evolution also shapes the fate of the Oort cloud. When the Sun's magnetic sphere contracts during quiet phases, it exposes more of the cloud to galactic influences. Over large stretches of time, this can alter the distribution of cometary objects, creating zones of heightened activity or depletion depending on the direction and density of external pressures. The structure of the Oort cloud is dynamic, constantly responding to both internal solar changes and external galactic forces, with the Sun's evolution acting as the central orchestrating influence. As the Sun brightens, the thermal environment of the Kuiper belt slowly shifts. Although these objects remain incredibly cold, even marginal increases in temperature can influence the stability of volatile ices. Some Kuiper belt objects may experience increased sublimation-driven mass loss, leading to minor shifts in mass distribution that affect their rotational states. Changes in spin can drive reorientation events, surface cracking, or the emergence of new jets, all contributing to the evolution of their physical characteristics. These cumulative processes demonstrate the sensitivity of distant icy bodies to long-term solar evolution. The Sun's changing output may also influence the collisional dynamics within the Kuiper belt. As radiation nudges smaller particles outward, the probability of collisions among larger objects may decrease gradually. Fewer collisions mean fewer opportunities to produce debris or trigger resurfacing events. Over time, this reduces the exchange of material between objects, allowing their surfaces to age and weather under cosmic radiation without frequent renewal. The result is a population of increasingly ancient, chemically altered bodies that record the slow, persistent influence of solar evolution across deep time. As the solar wind weakens in the future, the outer solar system will become increasingly exposed to galactic cosmic rays. These high-energy particles can penetrate deeply into the surfaces of Kuiper belt and Oort cloud objects, driving chemical reactions that create complex organic molecules. This slow but constant bombardment may darken surfaces or alter their spectral fingerprints, providing clues about both the Sun's weakening magnetic shielding and the history of cosmic ray exposure. Over immense periods, these surface changes accumulate to create distinct evolutionary markers tied to solar activity cycles. Some Kuiper belt objects may become dynamically unstable as the Sun's mass loss subtly alters the gravitational balance between the Sun, Neptune, and the belt. Orbits that were once secure may drift into interaction zones where Neptune's gravity can eject bodies or send them inward as comets. This slow diffusion process could significantly reshape the Kuiper belt's population. over time, creating patterns of migration that trace back to the Sun's evolutionary trajectory. These changes may also influence the supply of new comets entering the inner solar system during later epochs. The Sun's gradual expansion during its evolution into a red giant will eventually extend its influence physically into regions far beyond the current planetary orbits, though not as far as the Kuiper Belt. However, even the early phases of this expansion will generate increased solar wind intensity and luminosity capable of altering the orbits of Kuiper Belt objects. Enhanced solar radiation may induce more vigorous sublimation on larger dwarf planets, temporarily generating thin atmospheres that reshape surface features through seasonal processes previously impossible under lower solar irradiation. As the Sun loses mass more rapidly during its giant phases, its gravitational pull on the Kuiper Belt and Oort cloud will weaken considerably. Many distant bodies will respond by migrating outward, expanding the overall size of these regions. Some will escape entirely, adding to the interstellar population of rogue comets. This mass exodus marks one of the most dramatic long-term effects of solar evolution, as the outer solar system transitions from a structured reservoir into a dispersed cloud of wandering objects drifting through the galaxy. Interactions between the heliosphere and interstellar gas will also shift as the Sun evolves. When the solar wind becomes weaker and the heliosphere contracts, the boundary protecting the Oort cloud becomes more permeable. Interstellar gas may begin to infiltrate deeper regions, exerting drag on some of the smallest nuclei and altering their orbits. Over millions of years, this subtle process may redistribute cometary bodies, concentrating some regions and thinning others, all while gradually reshaping the structure of the Oort cloud. The Sun's life cycle affects the thermal stability of compounds within Oort cloud objects as well. Increased exposure to cosmic rays and interstellar radiation can stimulate slow chemical reactions that transform surface materials. These changes build layer upon layer of altered chemistry, creating a complex stratigraphy within each icy nucleus. Through these transformations, Oort cloud objects become time capsules that contain detailed records of both solar evolution and the cycling of galactic environments through which the solar system passes. As the Sun continues its progression toward the end stages of its life cycle, the outer solar system becomes a zone of heightened dynamism. Bodies previously locked in cold stasis may awaken under increased radiation or cosmic influence, creating faint sublimation tails even at unimaginable distances. These subtle activities hint at the pervasive influence of the Sun, demonstrating that even in its distant twilight, our star continues to shape the icy frontier of its domain. The Kuiper Belt may become more active, exhibiting temporary atmospheres or jets on select objects as solar changes ripple outward. Ultimately, the long-term evolution of the Sun will profoundly restructure the Oort cloud. As the Sun sheds mass, the gravitational threshold that binds the cloud diminishes, and many objects may drift away, turning the once vast cometary sphere into a loose and scattered remnant. External influences like passing stars, molecular clouds, and galactic tides will have a much easier time stripping away the weakened cloud. Over time, the Oort cloud may shrink dramatically or even dissolve entirely, leaving behind only those objects that settle into new, more distant orbits around the evolved Sun. Even after the Sun reaches its white dwarf stage, it will continue to exert influence on the remnants of the solar system. With its mass significantly reduced and luminosity greatly diminished, the new gravitational balance will encourage additional migration of Kuiper Belt and Oort cloud objects. Some may fall inward toward the faint remnant, while others drift further outward, forming an extended halo of icy material. These late-stage shifts reflect the Sun's final gravitational adjustments, highlighting how its evolution continues to reverberate through the outer solar system long after its main sequence life has ended. The cumulative effects of solar evolution on the Kuiper Belt and Oort cloud paint a picture of a solar system in constant transformation. Even the most distant icy worlds, seemingly isolated from the Sun's immediate influence, respond to its long-term changes with gradual but significant modifications in orbit, composition, and behavior. These distant zones act as sensitive seismographs of solar history, recording every subtle shift in brightness, magnetism, and mass over billions of years. Their evolution mirrors the Sun's, expanding, dispersing, and transforming in harmony with the star that has shaped them since the beginning. Introduce the concept of stellar winds and their increasing strength, slowly eroding planetary atmospheres over millennia. Stellar winds, the constant outflow of charged particles from a star's outer layers, represent one of the most persistent and transformative forces acting on a planetary system. Even when appearing gentle on human timescales, these particle streams exert cumulative effects that become increasingly significant over millions of years. As the Sun gradually evolves and its magnetic field fluctuates, the strength, density, and velocity of these winds shift in ways that subtly but steadily erode the atmospheres of nearby planets. Each molecule stripped away contributes to a slow but irreversible transformation, one that rewrites the environmental conditions of entire worlds across vast stretches of time. As the Sun grows older and more luminous, its internal magnetic activity evolves, leading to changes in the patterns and intensities of solar wind emissions. Regions of stronger magnetic turbulence produce denser currents of particles that travel outward at greater speeds, brushing against planetary atmospheres like a continuous cosmic breeze. While this process may seem negligible on a human scale, it acts with incredible persistence, gradually peeling away the upper layers of atmospheric gases. Over geological epochs, even planets with strong magnetic fields experience a consistent thinning that reduces their ability to regulate temperature, contributing to slow climate drift. Planets like Mars, lacking a global magnetic field, demonstrate the raw power of stellar winds in stripping atmospheres to near extinction. Without a protective shield to deflect charged particles, the solar wind interacts directly with the atmosphere, heating it and accelerating gases to escape velocity. Over billions of years, this relentless erosion transformed Mars from a planet once rich in rivers, lakes, and possibly oceans into the dry, thin-atmosphered world we see today. This transformation provides a powerful template for understanding how stellar winds may similarly shape the futures of other planets, even those currently protected by magnetic fields. For Earth, the presence of a magnetic field has long been a crucial defense against the Sun's winds, diverting most charged particles around the planet. Yet even this protective barrier cannot completely eliminate atmospheric escape. Tiny fractions of particles slip past the magnetosphere via polar cusps, carrying atmospheric atoms into space. As the Sun brightens and its winds intensify over millions of years, the rate of this leakage increases subtly. While Earth's atmosphere remains robust today, the gradual intensification of stellar winds ensures that the shielding effect will weaken relative to the incoming particle stream, leading to a slow, steady atmospheric decline. In the early solar system, stellar winds were far more powerful than they are today, driven by a sun spinning much faster and producing intense magnetic storms. This ancient, turbulent wind sculpted the atmospheres of the young planets, stripping volatile gases and influencing their long-term evolution. As the Sun ages, a new era of atmospheric erosion emerges, not from violent youthful bursts, but from the quiet and persistent strengthening of solar output. This shift highlights the dual nature of stellar winds, initially violent, later patient, but always shaping the atmospheres of the worlds they bathe. The increasing strength of stellar winds has dramatic implications for planets like Venus, whose dense atmosphere and lack of a magnetic field make it uniquely vulnerable to long-term erosion. Though Venus retains a thick envelope today, stellar winds have been gradually removing hydrogen from its upper layers for billions of years. This hydrogen loss helped prevent the formation of long-term oceans, accelerating the planet's transition toward a hellish greenhouse state. As solar winds intensify in the future, This erosion may continue to reshape Venus's atmospheric chemistry, potentially altering its already extreme climate even further. Even gas giants, despite their massive atmospheres, are not immune to the influence of stellar winds. While they possess strong magnetic fields that protect them from direct stripping, the immense surface areas of their magnetospheres interact with solar winds in ways that generate complex atmospheric dynamics. Over time, charged particles become trapped in their magnetic fields, driving chemical reactions in their upper atmospheres. As the Sun evolves and its winds change, these interactions subtly modify the composition and temperature of the giant's upper layers. Though not catastrophic, these changes accumulate steadily, imprinted across thousands of millennia. The slow erosion caused by stellar winds extends beyond atmospheric gases and into the ionospheres of planets, where charged particles interact directly with solar radiation. As stellar winds intensify, ionospheric escape becomes more pronounced, altering electrical conductivity and impacting the behavior of planetary magnetospheres. This creates a feedback loop where changing atmospheric composition affects magnetic shielding, which in turn influences the rate of atmospheric loss. Over immense timescales, such feedback can shift a planet from a relatively stable environment to one more vulnerable to solar influence, gradually transforming its entire atmospheric structure. Moons with tenuous atmospheres or exospheres also feel the cumulative effects of stellar winds. Bodies like Titan, Europa, and even Pluto experience atmospheric escape driven by solar-induced heating. Increased stellar wind activity over millennia enhances this escape, gradually removing volatile compounds from their outer layers. For moons with subsurface oceans, this loss may alter surface pressure and temperature in ways that subtly influence the long-term stability of their hidden waters. Though these changes unfold slowly, they collectively contribute to a gradual evolution of environmental conditions that shape everything from surface chemistry to potential habitability. In the distant outer solar system, stellar winds weaken significantly but still exert influence through the heliospheric magnetic field they carry. Over millions of years, fluctuations in this field can alter the rate at which charged particles enter the atmospheres of distant bodies. This process, though weak, can modify the chemical balance of these icy worlds, driving slow atmospheric erosion or alteration. As the Sun evolves and its magnetic properties shift, even the most remote planets and dwarf planets experience these gentle but persistent changes, demonstrating the far-reaching influence of stellar winds across the solar system. As solar winds grow stronger during later phases of stellar evolution, the heliosphere, the protective bubble formed by the solar wind, expands and contracts in response. These oscillations change how the solar system interacts with the interstellar medium. When the heliosphere contracts, interstellar particles infiltrate deeper into the solar system, colliding with planetary atmospheres and enhancing their erosion. This interplay between stellar wind strength and heliospheric boundaries adds another layer of complexity to long-term atmospheric evolution, particularly for planets at the edges of the solar system. When the Sun enters its red giant phase, stellar winds will intensify enormously, becoming thousands of times stronger than they are today. These powerful winds will strip the atmospheres of inner planets with ease, likely removing Earth's atmosphere entirely. As the Sun swells and its outer layers expand, these winds will dig deep into planetary atmospheres, leaving behind bare planetary cores or desiccated rocky remnants. This catastrophic stripping marks the final phase of atmospheric erosion, erasing the climatic histories of entire worlds in a relatively short astronomical period. The erosion caused by stellar winds also affects planetary surfaces by altering their exposure to radiation. As atmospheres thin, planets lose their natural shielding against ultraviolet and cosmic radiation. This increased exposure can sterilize surfaces, break down organic molecules, and disrupt chemical cycles essential for maintaining stable climates. Over millennia, This enhanced radiation environment contributes to the broader ecological decline of planets experiencing atmospheric loss, compounding the direct effects of erosion with secondary consequences that accelerate environmental degradation. Long-term atmospheric erosion also influences planetary water reservoirs. As solar winds remove hydrogen, a key ingredient in water, planets lose their ability to retain liquid or vapor phase water over time. This effect played a major role in the desiccation of Mars, and could eventually impact Earth as well if atmospheric escape accelerates under intensifying stellar winds. Over millions of years, this slow depletion of hydrogen can permanently alter the hydrological cycles of planets, contributing to their gradual transition into arid, uninhabitable worlds. Radioactive decay within planetary cores often contributes to the maintenance of magnetic fields, which counteract stellar winds. However, as planets cool and their cores solidify, magnetic fields weaken or collapse entirely. When this happens, the planet becomes dramatically more exposed to stellar winds, accelerating atmospheric loss. This creates a timeline where planets may remain protected for billions of years but eventually succumb as internal heat dissipates. The gradual weakening of planetary magnetic fields sets the stage for a late-life period of accelerated erosion driven by intensifying solar winds. Atmospheric erosion alters planetary climates not only by thinning air but also by shifting the balance of greenhouse gases. Carbon dioxide, nitrogen, and hydrogen escape at different rates depending on solar wind intensity and atmospheric composition. Over time, the preferential removal of lighter gases can enrich atmospheres with heavier molecules, leading to denser, hotter climates, or, conversely, removing critical greenhouse gases can trigger extreme cooling. These shifts can be subtle but eventually steer planets toward radically different climate states as stellar wind erosion compounds across millennia. The cumulative effect of stellar winds can also disrupt chemical cycles within planetary atmospheres. As upper layers are stripped, the mixing ratios of gases change, altering how sunlight is absorbed or reflected. This can shift temperature gradients, reshape weather patterns, and modify atmospheric circulation. Over long periods, these changes may cascade into major climate transitions, contributing to the slow transformation of habitable environments into barren landscapes. The long-term influence of stellar winds thus extends deeply into atmospheric chemistry, with repercussions that span entire geological epochs. On planets with thick atmospheres, the effects of stellar winds may take longer to manifest but are no less profound. Erosion gradually chips away at upper layers, decreasing overall pressure and altering the behavior of climate systems. Dense atmospheres may appear invulnerable, but even they succumb to the persistent assault of stellar winds over millions of years. As these layers thin, they lose their ability to trap heat or support complex weather systems, contributing to slow but irreversible climatic decline driven by stellar evolution. The relationship between stellar winds and atmospheric loss becomes even more pronounced in planets orbiting close to their parent stars. Though this is more relevant to exoplanets, the principle extends to Mercury and, to a lesser extent, Venus. Close-orbiting planets face constant bombardment from high-energy particles, leading to rapid erosion of any atmosphere they might possess. As the Sun evolves, even Mercury, long devoid of a substantial atmosphere, may experience increased sputtering effects, altering its exosphere and surface chemistry through enhanced solar wind interactions. The erosion of atmospheres by stellar winds influences the long-term geological evolution of planets. As atmospheres thin, pressure decreases, affecting volcanic outgassing and the ability of gases to remain stable at the surface. Over time, volcanoes may release gases only for them to be stripped away immediately, preventing the buildup of new atmospheric layers. This dynamic feedback loop gradually diminishes geological climatic coupling, pushing planets toward increasingly stagnant environments where atmospheric renewal becomes almost impossible. Surface temperatures also shift in response to atmospheric thinning caused by stellar winds. Reduced greenhouse effects may cause planets to cool, while decreased atmospheric density can lead to extreme temperature swings between day and night. These fluctuations stress planetary environments, altering thermal expansion patterns in rocks, increasing erosion rates, and contributing to the slow geological reshaping of planetary surfaces. As stellar winds intensify over time, these temperature variations become more pronounced, feeding into the complex network of changes that drive planetary evolution. The long-term rise in stellar wind intensity also affects how atmospheres interact with solar ultraviolet radiation. Stronger winds correlate with increased UV flux, which breaks apart molecular bonds in atmospheric gases. This photodissociation accelerates the loss of hydrogen and other light elements, amplifying the erosive effects of the winds themselves. Over millions of years, this combined assault becomes one of the most powerful agents of atmospheric transformation, gradually pushing planets toward thinner, more fragile atmospheric states. The slow but relentless erosion caused by stellar winds paints a future where planetary atmospheres become increasingly vulnerable. Even Earth, with its magnetic field and dense atmosphere, faces a distant future where the sun's intensified winds and radiation overwhelm its defenses. While this process unfolds on timescales far beyond human lifetimes, its inevitability demonstrates the profound influence stars exert on their planets. Worlds that once teemed with potential may find their skies thinning, their climates shifting, and their surfaces exposed to the harshness of space. In the end, stellar winds act as the breath of a star, gentle, persistent, and transformative. They sculpt the atmospheres of planets over billions of years, leaving behind worlds that reflect the full story of their parent star's evolution. From the gradual thinning of protective layers to the final stripping during a star's death throes, stellar winds shape planetary destiny with unwavering patience. Their effects accumulate across millennia, weaving the intricate narrative of how planets evolve, change, and eventually fade under the influence of their star's inexhaustible power. Discuss the subtle but cumulative impact of gravitational interactions as the Sun's mass ever so slightly decreases. As the Sun continues its long, steady process of nuclear fusion, converting hydrogen into helium and releasing radiant energy into surrounding space, it very gradually loses mass a tiny fraction each year, yet a loss that is relentless and irreversible across astronomical timescales. This decrease in mass weakens the Sun's gravitational grip on the solar system, and although the change is almost imperceptible in any single human lifetime, it acts like a silent sculptor over millions of years, slowly altering the orbital characteristics of the planets. Even a fractional reduction in the Sun's mass means its pull slightly relaxes, allowing planetary orbits to drift outward, elongate, or subtly shift in resonance patterns that have been stable for eons. This gradual drift outward is not dramatic in the way that catastrophic celestial events are, but its importance lies in its cumulative nature, the kind of creeping change that is only visible when comparing distant epochs. Earth's orbit, for instance, expands by centimeters to meters per year, an amount undetectable without precise measurements but significant when multiplied across millions or billions of years. As the solar gravitational well becomes shallower, the delicate dance between orbital periods, gravitational interactions, and resonance stabilizers begins to evolve, sometimes in ways that promote stability and other times in ways that could destabilize long-established patterns. In addition to driving outward migration, this mass loss influences planetary eccentricity, subtly modifying how stretched or circular an orbit becomes. The planets respond not just individually but collectively, because the solar system is an interconnected gravitational web where small variations in one location can ripple outward and influence the architecture as a whole. Resonance pairs, planets whose orbital periods maintain whole number ratios, may shift slightly out of tune, altering how they exchange angular momentum. These shifts are minute but persistent, and over long intervals they may accumulate into significant architectural reshaping. For the giant planets, which dominate the system's gravitational structure after the Sun itself, the Sun's mass loss has intriguing consequences. Jupiter, being the most massive, becomes relatively more influential as the Sun weakens, subtly changing the balance between planetary perturbations and solar centrality. This means that Jupiter's gravitational influence may grow proportionally stronger in governing the motion of asteroids, comets, and even the orbits of Uranus and Neptune, thereby altering the solar system's long-term dynamical stability. These shifts can redirect small bodies, increase scattering events, or alter stability zones in ways that aren't immediately noticeable but play out over deep time. The Kuiper Belt, already a fragile and dynamically tenuous region, may experience increased dispersion as solar mass loss reduces the gravitational cohesion that keeps its objects loosely bound. Orbits at such vast distances are particularly sensitive to small changes in gravitational parameters, meaning that even slight decreases in solar mass can expand the region, increase orbital periods, and cause more objects to wander or drift into different dynamical classes. This can lead to a slow thinning of the belt, a gradual spreading, or an increase in interactions between objects as they drift into overlapping orbital paths. Beyond the Kuiper Belt, the Oort cloud, an enormous, diffuse sphere of icy bodies extending nearly a light-year, may be even more profoundly affected. The Sun's grip at these extreme distances is already tenuous, only barely preventing interstellar tidal forces or passing stars from stripping objects away. As the Sun continues losing mass, more of these distant cometary fragments could slip free, effectively increasing the frequency of Oort cloud escape but decreasing its long-term stability. Over hundreds of millions of years, this could meaningfully alter the rate at which comets are injected into the inner solar system. The gradual loosening of solar gravity also affects the orbital resonances that help maintain planetary spacing and prevent chaotic interactions. With the Sun's mass slowly declining, some resonances weaken or shift position, altering the delicate balance that keeps the inner planets separated and stable. Over extremely long timescales, this could theoretically open pathways for small instabilities to grow, though not enough to cause planetary collisions. They may still influence long-term orbital eccentricities or inclinations. Another subtle effect of the diminishing solar mass is the slow change in the barycenter, the system's gravitational center. As the Sun grows comparatively lighter relative to the massive outer planets, the solar system's barycenter shifts slightly, causing the Sun to wobble differently in response to planetary movements. This wobble doesn't meaningfully alter planetary orbits directly, but it adds another layer of dynamical complexity that compounds with other factors to influence long-term evolution. The asteroids within the main belt, lying at a dynamic crossroads between Jupiter and Mars, are particularly sensitive to resonance changes. As Jupiter's influence grows proportionally stronger due to solar mass loss, certain resonant regions may expand or contract, gradually pushing asteroids outward or inward. This may slightly increase the rate of asteroid migration or introduce new chaotic pathways through which asteroids shift between orbital families, potentially influencing impact probabilities over extremely long cycles. Similarly, the Trojan asteroids, clumps that share Jupiter's orbit, occupy gravitational equilibrium points dependent on the balance between Jupiter's mass and the Sun's. As this balance shifts, the stability of these points may adjust, altering how tightly those swarms remain clustered. While a collapse is unlikely, a gradual spreading or reorganization of Trojan populations is plausible. Satellites orbiting planets, particularly the tenuous outer moons of Jupiter and Saturn, may also experience slight alterations as planetary motions adjust to the new gravitational environment. These moons may feel minute but non-zero changes in orbital perturbations as the planets slowly drift farther from the Sun and gravitational harmony shifts around them. The cumulative result may be subtle shifts in orbital eccentricity or inclination over immense spans of time. Cometary pathways, especially those originating from long-period comet reservoirs, may be influenced by both the weakening solar gravity and the growing relative influence of passing stars. With less gravitational hold from the Sun, such comets may become more susceptible to external perturbations, potentially increasing the proportion that escape the solar system altogether. This reduces the long-term supply of inward-falling comets. Long-term climate effects also tie into gravitational changes. As planets drift outward and receive slightly less solar energy, their equilibrium temperature shifts. While the effect is extremely small compared to other climate drivers, over hundreds of millions of years it contributes to slow planetary cooling trends, especially for those already at the edge of the solar warmth threshold. Planetary ring systems, too, could experience changes as the solar gravitational gradient weakens. While rings are primarily shaped by their host planets, the Sun still contributes tidal effects that subtly influence ring structure. As this diminishes, certain ring regions may experience slight redistributions or changes in dust retention. Over very long timescales, orbital resonances between the giant planets may shift enough to alter the spacing between them. Even small adjustments might cascade into broader dynamical changes that modify the architecture of the outer solar system. These are not catastrophic events, but are the quiet, gradual reshaping typical of a maturing star system. For the inner planets, the outward drift may marginally increase orbital separation, reducing gravitational interactions between them. This could promote slightly greater long-term stability of their orbits, though this is balanced by other destabilizing forces acting on geological timescales. The slight reduction in solar mass also affects the solar tidal forces acting on planetary interiors. On Earth, these tides contribute subtly to geological stress patterns. A minute weakening over time shifts how energy is distributed within the crust and mantle, although the effect is extremely small compared to tectonic and geothermal forces. Interplanetary dust dynamics shift as well. Dust spirals inward due to pointing or Robertson drag, but with a weaker solar gravitational pull, the rate of inward migration changes slightly. This can influence dust density in the inner solar system and alter long-term patterns of zodiacal light and dust deposition on planetary surfaces. The gravitational sphere of influence of the Sun, its Hill sphere, also shrinks gradually. This decreases the region where the Sun can effectively retain objects, making it easier for distant bodies to be perturbed away and weakening long-range stability. This shift subtly modifies how the solar system interacts with the interstellar medium. Even spacecraft trajectories, over century-long missions, could experience minute differences from expected paths because calculations assume a constant solar mass. The gradual shift affects long-term path projections, though the effect is tiny and generally corrected for in modern navigation models. Looking still further ahead, as the Sun continues losing mass more rapidly in its red giant phase, all these subtle effects become dramatic. Orbits will expand significantly, resonances will break, and entire architectures will shift more rapidly. The quiet, almost gentle changes occurring now are simply the earliest hints of the Sun's far future transformations. Ultimately, the Sun's gradual mass loss is a reminder that even the most stable cosmic environments are always in motion. Planetary systems are not fixed, but dynamic ecosystems shaped by slow forces acting across time spans that dwarf human history. The weakening of solar gravity is one of the most silent but influential of these forces, a constant undercurrent guiding the solar system's choreography as it evolves through the ages.